video.
Thank you. So you're a director as well as a
There we go.
engineer.
No.
Okay,
All right, are we on?
We're rolling.
All right, so we're here, going deep. We're still in the kernel, and we're with Landy Wang, and he owns the memory manager. So, can you tell us a little bit about yourself, what you do?
I work on the memory manager in NT.
Here, you want what you mean?
Okay.
That's just the direction style. That would.
That's fine.
Thanks.
So I work on the memory manager in NT and help evolve it, make Windows do everything that everybody wants, and chase down all the hard problems on the way.
Memory leaks, that type of problem.
Memory leaks aren't usually as bad, but memory corruptions are harder. You see some data doesn't have the right value, but it's long after the fact, so you kind of have to try and reconstruct what happened.
So, what is the memory manager?
Memory manager, simplistic overview, is a way that we provide. It's a subsystem that provides facilities and abstractions to consumers of them up above. So you can think of it as a layer between the hardware and between device drivers and applications, such that they're not exposed to the nuances of hardware. As hardware evolves, it just all works for them, and we take care of all the stuff in the middle to glue it all together.
So allocating memory, deallocating memory, allocating pages, that kind of stuff?
Sure. Someone says, I want to allocate X, I want to use it for some period of time, and then I want to free it. And we handle the bookkeeping chores associated with it.
Okay.
On a simplistic level.
And of course, if someone doesn't free an allocation, in other words, you need direction from a consumer. So in other words, I'm way up in user land,
Okay.
and I allocate, spin up a thread. So I'm now working with you, I'm assuming, memory manager. You're going to allocate some memory on my behalf.
Mm-hmm.
So I tell you, I ask you, allocate this much memory, and you do it for me.
Sure.
I'm a forgetful programmer, and I forget to deallocate the memory. And so now I've opened up a potential memory leak or whatever.
Sure.
The memory manager waits for me to signal a deallocation as opposed to go, well, hey, you haven't, what's going on up there? I mean, I imagine there's not that kind of thinking or logic at that level. Is that something how the memory manager may evolve to that, or is that just...
Well, there's a couple of different
Thanks.
aspects that this leads into. So one is, if a process allocates memory and we give it to them, whatever the memory's for, creating a thread, creating a process, whatever, it doesn't matter, it's all just memory. When he's done with it, he can free it.
Mm-hmm.
If he decides to never free it and just hold on to it forever, it'll consume space in his address space. You can analogize this to your refrigerator. You can keep buying food and putting it in the fridge, and one day you'll run out of space in your fridge, and then you'll realize, hey, I got to throw away my old moldy food.
Exactly.
Or I can hold on to it and not put anything else in my fridge, and I probably won't be very happy, right, at the end of the day. And so that's what we do. We let you hold on to this memory for as long as you want. Once the process exits, we make sure we clean up any mess that he left behind and throw it away from him. So if you move from the house, we'll clean out your fridge. Otherwise, until then it's your house, and whatever you want to keep in it, you still got a fixed size fridge, and you're going to have to live with however happy or unhappy you are in that. As far as us proactively cleaning out your fridge when you're not looking, we do that with your physical pages, but at a virtual level, your space is still consumed, and you can't use it. And we clean out your physical space without you knowing it. So that way we make you a good citizen with everyone else. As far as cleaning out your virtual space, that isn't something we do in the kernel, but what we do is provide technology to people like the CLR group so that they can do this write watch, type of automatic coalescing, garbage collection of unused blocks and get rid of the virtual space. So, we provide technologies to do either of those.
Excellent. So you provided that, so I could write my own garbage collector on NC because
Correct.
of the facilities you've offered me.
Correct. And that's what the CLR team does, for example. So that's one of the benefits of managed code, right? That you don't need to allocate, use it, and then free it. You can allocate, use it, and forget it, and they'll clean it up for you.
Absolutely. And you don't see a day where that could happen down in the kernel.
It's
It'd be too hard.
It's a lot of CPU time. There's a lot of cost as well as memory cost to try and figure out, hey, is it automatic? And should we just clean it up for you? So I don't think that we would incur that cost, but never is a pretty strong word. Anything
Sure.
is possible.
Excellent. So, how long have you been working on Memory Manager?
Well, I've probably been working on operating systems since the early 80s.
Wow.
So it's been a long time. Different pieces, but it's what I like to do, so
Sure.
it's a good fit.
Excellent. Has the NT Manager, Memory Manager evolved since 3.5?
Yeah, we've changed it a lot.
Okay.
There's been a lot of changes that have happened. It's probably grown very significantly, probably 4x the size in terms of code from NT4 to today's operating systems. So it's a huge amount of new features and facilities and tricks that we do to make things run smoother, better, easier.
Sure.
But without the code bloat that comes with something when you hear something is 4x bigger, you think, wow, there's a lot of stuff in there maybe that we don't need.
Yeah.
But we're pretty slick about all that stuff. We
Sure.
throw away the stuff that we don't need, so basically tailoring each operating system to what the person's doing as opposed to a one-size-fits-all.
But in essence, you are so you're a shared component that everyone depends on. Everybody, including
Correct.
kernel components.
Correct.
So if I'm a kernel component or a user component, and I need memory, I'm talking to you.
Eventually it will come to me.
Yeah.
At the upper levels, and people will front it, basically, user mode heap implementation, for example, would only come to me every so often. So it might allocate a big chunk and then dole out parcels without coming to me for every subsequent request.
Okay.
And going back to our fridge thing, it's like you stock your fridge
Yeah.
because you don't want to go to the grocery store every time you want a sip of milk.
Yeah.
But ultimately, you're going to come to me at the grocery store to get the milk. You may hold cartons and cups in your house, in your fridge,
Yeah.
but when they run out, you'll have to come to me for more, and I'll give it to you. But, there's certainly things people do up above me, so they don't have to come to me all the time.
So what are some of the biggest challenges or really interesting, I don't want to say problems, but just the space you're in to be this shared component that's needs to be incredibly performant, needs to be predictable, right? When I say release this memory, I'm expecting it to happen. When I say allocate this memory, I'm expecting it to happen. Now, are you the guy that also surfaces out of memory exceptions? I mean, how does that work? I guess so. This is kind of random thing. So
Sure.
Let's stick to the first question. What are some of the challenges of writing this shared component that everyone has to rely on? The whole system relies on memory. Without memory, nothing happens, right?
Yeah,
Pretty much.
without memory, nothing happens. But there's a lot of facets of the system where
Sure.
without a CPU, not a lot happens either. Right?
Understood.
In that sense, it's the challenges are, I wouldn't necessarily call them challenges. I tend to think of it as more the stuff that's interesting about the job. What I like about it is that you get to work with a wide spectrum of people and their needs. On any given week, I'm working on something different, on a bunch of things that are different. You're multitasking a bunch of different things, but one week it might be working on something like, resume from hibernate on your laptops faster. That next afternoon, you might be working on some network optimization to help them do a zero copy stack. The day after that, you might be scaling a terabyte size system, and the day after that, you might be figuring out how to make NT run on a slot machine in Vegas.
Wow.
To running a telephone system, on a big server. But it's always different because there are so many different needs of people, and places to use NT, such that they need to evolve the system in a way that we hadn't thought about before, or that you couldn't have predicted before. And so I get to work with a lot of very smart people inside and outside of Microsoft, who have needs and have ideas on things they want and how to do them, and it's neat making all these things happen.
Fantastic. That's great. So we talked about memory leaks earlier, because that's really a problem with the consumer, right? Or the allocator.
Sure.
So in other words, so can we talk about what a memory leak is? First of all, we hear the term a lot. So is you allocating memory and not deallocating?
Right.
Is that how it works?
Sure.
Okay.
And at some point, when you never deallocate, you run out of everything that's left, right? The pie is only so big, and you keep allocating and never freeing. Eventually, there's no more slices in the pie, and that's when someone notices and says, I can't get any memory.
Okay. And the memory manager like, all right. So the memory manager doesn't have any sort of way of determining that a memory leak is happening in the system. So in other words, let's say that I'm this bad programmer, or just a programmer that's forgetful, and I've allocated all this stuff, and I've not deallocated, and I happen to be running, say, like a service or something, and so my process just keeps running, and all of a sudden things start slowing down, etc. Is there any sort of monitoring that happens down at that level? That like, hey, something's going on here,
Sure. I mean, I think the way to conceptualize it is that you can't run out of physical pages because we take those from you without you knowing we're doing it.
Okay.
Right. That's part of this whole virtualization of memory. Right. That apps don't really know how much physical memory they have right now. They know how much virtual memory they have. Right. The machine has 512 meg of RAM, and you have some app that uses a gigabyte. Now, he doesn't know that there's really only 512 megs, and that we're doing this juggling act to make it appear to him that he's got a gigabyte, but he doesn't really. Right? If he ever came to us and said, I want the whole gigabyte right now, well, there really isn't a gigabyte. So instead, we dole it out to him in pieces, and he doesn't know that this sleight of hand thing is really happening. So we can always take back the physical memory from someone, and therefore the penalty typically becomes his virtual address space. He runs out. He's got nowhere to put all this memory because he's never freeing any of it. Right? And so he feels the pain, but the next guy in line doesn't. Right? You don't clean out your fridge, it doesn't really hurt your neighbor. Your neighbor still eats good. You're not eating so good, but he's eating fine. Right? The only where the issues more come into play are where there's a shared resource. That there's only so much physical memory plus page file space to create this virtual memory illusion, and that you might eat more than your fair share. Right? And then we have these tools that track that down. You can see how much any given customer is using. So you can say, hey, why does this guy have so much? What's he doing? He must be leaking it.
True. And I've also noticed on NT, as an administrator, I can change my page file size.
Sure. So if you want more, it turns out, hey, this guy says, hey, I really do need all this bad food in my fridge. It's important for me to keep for science experiments to see how much mold I can grow in 6 months.
Yeah.
Then you can up your page file size so that you get more virtual memory for everyone else.
Cool. So, that really raises a good point. Can we dig in a little bit to this virtual versus page file? Like, we hear page file all the time. Can we really talk about what it is? Like, what is the page file? Like, what is it? That's my question.
Sure. Okay. Think of the page file as just a file on disk.
Okay.
Where we store pieces of memory because we need to make space. Right? So one way to think of it is, hey, you have food on your counter and food in your fridge. Right? You can't fit all the food from your fridge onto your counter. The counter's not big enough.
Okay.
So you rotate some of the food from the counter into the fridge, then back out to the counter, and back into the fridge, such that whenever someone comes along in your family who's hungry, there's food on the counter for them. Now, the whole fridge isn't emptied on the counter, but the food is on the counter. So when it's breakfast time and he wants breakfast, you rotate out some breakfast food, and the lunch food sits in the fridge. When lunchtime comes along, you juggle it around, and the lunch food is out, and the breakfast food is in the fridge. So you're playing this juggling game, and you can think of the refrigerator as the page file, right? It takes longer to get the memory out of there when someone wants something, but it's a place where you can hold it where it won't go bad, where it won't spoil, you won't lose the bits.
Okay.
Right? And so when someone wants it, part of memory management's job is to, if we can, predict in advance and get it out before people show up at 12 o'clock. And for stuff that we couldn't predict, that this guy wanted ketchup, on his ham sandwich. Mm-hmm. Well, we go and make a quick trip to the fridge and pull it out, the fridge being the page file. So we do this juggling act of telling a guy, hey, the food here is unlimited. Breakfast, lunch, dinner, whatever you want, whenever you want it, it's all here. And we do this juggling act of hiding it in the page file when it's not being used and bringing it out when it is. And that's all the page file is a place to put the RAM that doesn't fit right now.
And you store it on the physical hard drive.
On the physical
hard drive. So, of course, you're limited to the speed of the disk.
Right, so the disk being a mechanical device is much slower than the purely electrical DRAM.
Understood. And you keep that for the major intensive.
So the stuff that's frequently accessed, we'd much rather keep in DRAM. That's part of the memory management algorithms. We try to keep the high access stuff around so it can be available very quickly.
And how do you determine high access stuff? Like,
we get hints from the hardware. They set access bits on various pages as the CPU fetches them, and so we age them accordingly and try and use that. We also try to predict based on what we see you do. If you're reading a file sequentially, and we might realize, oh, you've just read the first page and the second page, you're probably going to read the third, fourth, and fifth pages. Let's look at them now. Now you've read the first 5, you probably want an even bigger stride, maybe even more, that kind of thing. So we try to look at what you're doing. We try to look at what you used to do before. We try to figure out, what are you accessing.
Excellent.
Make it all balance out.
Sounds pretty complicated algorithms. What language do you write in?
It's almost all in C. A little bit of assembly here and there, but almost all in C.
Okay. Interesting. And what do you think, sir? Do you have any good questions? We're here with Michael Lehman. He's also on my team. He's a developer.
How do you go about trying to optimize the performance of the memory manager? What kind of test suites of applications or other tools and things do you run to benchmark what you're doing?
So that's an interesting question. How we improve the speed of NT. We're very fortunate here at Microsoft. Unlike a lot of small companies that I've worked for, we have a huge group that does nothing but performance. Who are happy to give me numbers and tell me, where we're regressing or where we're really improving, and we can make changes and tell them, hey, we made this change. We think it's going to make a big difference here, and they'll check it out and say, wow, it really did improve this scenario benchmarks, or degraded these, and they'll give us lots of data on why it did or why it didn't, that we can then piece together and figure out, what we need to make better, or what we, step backwards on by accident, and get a handle on things. And the other advantage of being Microsoft is we have no shortage of people inside and outside the company to tell us when we're doing something poorly, or doing something great. And so, we get a lot of feedback from a lot of people that we can use constructively to really improve things quickly. So that's a luxury that we're fortunate for.
Certainly.
Were there a lot of changes involved in moving to the sort of more of virtual processors in terms of memory management, in a virtual PC, virtual server, as opposed to running on the real hardware from the memory manager's point of view?
There's not a lot of changes to running a virtual PC, basically the hypervisor type level that's shimmed in between the hardware and the operating system. It's really, the onus on that is really on the hypervisor guys. If you want to put a shim in the middle, you got to make sure it presents the same look and feel as what the real hardware provides. If you want to put a shim in between your rest of your car and the driver, you got to make sure the gas is still on the right, the brake's still on the left, and the steering wheel, when he turns to the left, the car turns left, and if he turns to the right, the car turns right. And that's their job more than ours. We make changes to help them make Windows a better client of their shim. That we can perform some operations in a different way such that they can virtualize it more efficiently and not take as much overhead to perform the virtualization. But to us generally, if we make no changes at all, we would still run. So any changes we make in the area of virtualization end up being gravy, right? Things that we can make better and make things work better, make features or things possible that weren't possible before by doing them in a way that they can leverage what we're doing.
So now, in terms of the virtual versus page file system, on a 64-bit machine, you're now probably going to have to spend less time worrying about the juggling between page file and because now on 64-bit you can have much more RAM than 32-bit supports. Correct? And so is that going to be? And do you make any adjustments to that, or just you play in that field already? Not a problem. More virtual space, rock on.
Sure.
Algorithms take care of that.
Sure.
So essentially, which might partially have to do with performance increases overall for certain applications on 64-bit. Is that true?
We had to make a bunch of changes to evolve to 64-bit.
Okay.
Right. And we started fighting that off more than 8 years ago, probably.
Sure.
Right. Such that we can handle things more efficiently, because now you have different data structures where before might have been limited to a couple of thousand, might now have hundreds of millions of entries because the address space is so much bigger that we decided to employ And so, I mean, there have been a bunch of algorithmic changes such that we can traverse things, more intelligently, where the price on 32-bit was small but not zero, and on 64-bit is huge. And so if we don't evolve, then that huge price is too much, right? So there have been a lot of changes, but the intent being that almost all the changes that were necessary for 64-bit would also help 32-bit. Sometimes not as much, sometimes just as much. And 64-bit, was the driving factor in some of those changes, but it doesn't mean that 32-bit didn't benefit from it. We decided to keep the exact same source code base for both, with clever if defing, and then this maximizes our code coverage, such that if, no matter what type of machine, is more prevalent at the time, we still get common coverage across the whole code base. So any bugs we fix, get fixed in all releases instantly. You don't have to do 3 different fixes for 3 different architectures and that kind of thing.
Fantastic. That's great. It also makes it through the transition to run 32-bit apps in a 64-bit environment, right?
Sure.
So how do you control? The memory manager will control that process A doesn't overwrite process B's allocated memory, correct? So you're watching that to make sure that can't happen.
Unless process A wants it to. Right? You can collaboratively share things. Process A can say here's some shared memory. Totally. There's other guys who can use it too. But I mean, clearly, if it's memory he does not want another app to access or modify, then we provide them protection.
Understood.
Are there any new hardware advances coming out that are going to change memory management, things like execute protection and things like that get into the level that you're dealing with?
Sure. I mean, we have lots of, that's one of the neat things about working in memory management is that we have a lot of evolution always going on. It's not a static part of the operating system. There's always hardware advances coming out, always things that we could change for. It's hard to always predict what they are. Some of the things we can because, a lot of times people come talk to us first and say, hey, do you think this is a good idea? This idea at all, or this way we're choosing to do it? And would Windows work with it already? Could it be made to work with it? What's entailed? So we have lots of conversations like this with different, people. And if you look back on what NT could do back in NT4 versus today, there's a huge variety of different hardware, both in terms of scale up and scale down, as well as capabilities that we do in Windows that we couldn't do back then.
Interesting. Very interesting. So you work a lot with the cache manager. So basically everything will come through you when having to deal with so file I/O, for example, will work with you to allocate memory for a write, right,
Okay.
etc. Do you make optimizations for the kernel components? Do they have a different set of APIs they can call, or not? I guess I kind of know what I'm asking, but
Sure. We make changes for kernel components in the sense that in a number of cases they can bypass validation and so on because they are trusted components. We believe that the cache manager has access rights to the file it's trying to write. It validates them. It's not that no one validates, it's that they're vouching that, hey, we've already validated it. So we can skip a lot of stuff in memory management when we know it's the cache manager calling, because he's saying, I've taken care of this already, you don't need to do it again. And so we can shortcut a bunch of things and make various optimizations. From the memory management perspective, the cache manager is really just a client of it, the same thing as an application would be. The cache manager is something that manages on a virtual basis file I/O and maps those views in and out of the system address space. The same way as an app would do, where they want to map things in and out of their address space to handle their I/Os. So while for memory management we provide the cache manager with specialized interfaces so that it can be more efficient at this, at the upper levels, at the lower levels of memory management, he's really just another client. And we fetch pages for him just like we do for anyone else, materialize them, trim them from him, and so on.
Mm-hmm. So is there any, so you were at WinHack talking to device driver developers, clearly interested in this technology. What sort of feedback did you receive? We can talk about Longhorn, I'm assuming, since
Sure.
you talked about it at WinHack.
I'm not sure how much. I know that the WinHack talk was under NDA.
Okay. Oh, it was. So we won't talk about it then. Sorry, folks. We'll cut that for PR, but that's fine. Someday it would be nice to know to talk about the Longhorn Memory Manager.
Sure.
When we can.
I think there's been a lot of neat changes that will make a big difference to a lot of people.
Fantastic.
That we'd be happy to talk about.
So you mentioned hibernation, standby. How does that work? I mean, are you taking all of the state, sticking it into a page file?
Basically.
That's what you're doing?
Basically.
Okay.
Or in the case of standby, it's just sitting in memory, and we pop back up to where we were.
So it's sitting in RAM?
Right. I mean, we just keep the kernel image the same depending on whether you're standby or hibernate. But I mean, yeah, I mean that's the basic idea. That when you hibernate, that we're going to write it out to disk, and later on when you boot up, instead of having to load everything fresh, you just go get this one image from disk, plop it down in memory, and jump to it and say, I'm back.
Cool.
And pick up where I left off.
Now let's assume that the unbelievable happens and the system crashes. Would it be possible to do the same sort of thing? So, for example, I'm working, right?
Mm-hmm.
I go to get a cup of coffee. It's 2 in the morning. I set auto update to automatically install, update and install. The critical patch comes out, or whatever, but it has to reboot.
Sure.
Because I have DLLs loaded in memory, have to reboot to make sure everything's cool. I come back, and my computer's rebooting.
Mm-hmm.
So, and of course, what I was working on wasn't saved, and the state wasn't saved, etc. Is it conceivable that everything that as it was at that point could be stored into a page file before reboot? Does that make any sense at all? Or
Sure.
some sort of
It depends. It's,
image?
Yeah, it depends. I mean, on where the crash was. If the crash was in the disk driver, that would write the pages out to your page file, and now you can't write anymore,
Sure.
you might have problems. If it's in the file system and the blocks are mapped wrong now due to a memory corruption, and so when he thought he was writing the page file, he was really overwriting a picture of your kids. You know, that would be useful to put there. So writing out during a crash is something that, in a lot of cases, you're going to be pretty wary to do.
Understood.
You know, as far as thinking, hey, you can just resume right where you left off. I mean, presumably something went wrong, and you don't want to resume back at that point again. You need to figure out what went wrong and fix it,
Yeah.
and then put it all behind you for good.
True. Now that I can understand the case of a crash, but in the case of, let's say I'm a system updating service, and I know it's, you know, obviously it's really hard to tell whether or not a reboot is going to be required, but let's pretend that I can figure out whether or not this DLL that I'm replacing is actually loaded in memory, so I know that I'm going to have to reboot depending upon what it is. If there was some way for me, before I call into the reboot of the system, I could say, save state.
Except for the DLL that you don't want to save state for, so save some of the state,
Yeah.
but not all the state.
Sure.
And then some of the
Complex.
actions that the prior DLL did, that the new one wouldn't do, you want some of those actions undone.
Yeah.
And some of these images saved, and some of the ones you loaded to not load, it ends up being a slippery slope. That you,
Absolutely. Well, that's good that we're talking about it too, because a lot of people question, like, how come we can't do this, right? How come, you know, you restarted the system and it doesn't just come back to where it was? Because I wasn't ready for it to restart.
Right.
But it's good to talk about why it's complex.
Sure.
So
I
that's
mean, nothing's impossible. Well, maybe some things are impossible, but
yeah.
you know, it's sometimes it's not as easy as it looks when you first set out for it.
You think it'd ever be possible to do idle mode hibernation? In other words, you know, I've gone off to get the cup of coffee and got, you know, tied up watching Jon Stewart on The Daily Show, and have the system sort of take a hibernation snapshot, and then it crashes on me later. My kid knocks the power plug out. When I come back, I'd like to go back to the last thing, but just have it do it kind of automatically, like Office saves backup copies of the documents as you work. Think it's ever going to be possible to have the whole system kind of save a backup state of where it was, so you don't have to start completely from scratch?
Well, you're probably talking to the wrong guy here, but that won't stop me from answering your
Fantastic.
question. There's a lot more to saving state in the sense of how much do you save, right? And that's a different group of Microsoft that does that. The memory manager doesn't really play a part in most of this, other than it's the low-level messenger who reads and writes blocks. But in this kind of scenario, you wouldn't be the decision maker. He's just the messenger. And the decision making is more complicated because you could say, you know, taking your case of, hey, you know, save it when I go get my cup of coffee at some point. But now there may be things saved that weren't part of your intent to save, right? Other actions that are going on in the system at the same time. And so now you're saving partial state, right? You write out some of your files that are half done, you're halfway through a sentence and it gets saved. And then you come back and we save another snapshot later. So you have these multiple snapshots built up that may constitute multiple files, not just the one you're working on, right? But you may have had your Internet Explorer browser pulling into cache some other files. And now you have some of those that are half pulled in. Some of your Word documents you're working on right then were half pulled in. You know, it's hard to say, right? Some other download or some update that you were downloading, you know, you have half of that saved. So you might get pieces of multiple different actions that you've triggered or that your computer is set to auto-trigger, like your 2 a.m. update thing that you were talking about. And you'll have pieces of all these things saved. And then you have to parse through the snapshot to decide, hey, which pieces of these do I really want to roll back, and which ones do I really want to roll forward? What about ones that I sent over the network? What if I updated some file over the network, and so now it's on a different machine, and I updated it with a message that said, hey, John, I'm done looking at this file. All right? The machine crashed, and now you want to roll back. How do I roll back that message that I already sent to him? What if John's already read it?
Yeah.
You know, but now I'm taking that back. I don't really want to be done. How do I tell him when done? And so there's a bunch of complicated issues that I think arise out of that type of scenario, such that it really works, as opposed to it only works with a bunch of caveats, you know, that the average person, you know, doesn't think about and shouldn't have to think about.
Agreed. I mean, and the other part is that in many ways it should really be responsible to an application, right? So if I'm in an application and something changes, the application should be able to deal with, and it does, many do, will save last, like Word will do that, right?
Sure.
You're writing a letter and something happens,
Sure.
whatever it is. Some other app causes Word to crash or something, and you can launch up Word and you can go to get where you just were, because it's smart enough to know, okay, something's happening, save, or it does saves periodically or whatever.
Sure.
It's all interesting stuff, and I understand it's outside of the realm of the memory manager, but it's just a very interesting construct, because, you know, we often take the stability of the system for granted, and writing stuff and allocating objects and all this stuff, and it's just happening. So you deal with tons of processes, right? I mean, tons of threads. And how many threads are you usually dealing with every? That's a hard question to ask, but like a lot of threads in Windows. Threads are the core construct of something happening on our operating system.
Sure, you're one of them.
And probably will be for a time to come. They don't have to always be, but they are for now.
Okay.
So you as a memory manager, anytime you're dealing with all threads on the system, allocating, deallocating on their behalf, and the processes which are constructs that are made of multiple threads, etc. Let me ask you this: he mentioned earlier about hardware changes. Let's talk about multi-core. Does that have an effect on what you do in any sense, or is that really just further up the stack, and it just means that I have to know how to write good multi-threaded code? So does it affect the way you interact with the system?
I think at this point it doesn't affect how the memory manager interacts today. It's hard to say if in the future that'll still be the case. We may think of some creative way that it could interact. In general, I mean, the memory manager provides these facilities and optimizes the system such that, you know, consumers of these facilities run efficiently. But the same facilities we would have to provide for SMP, we have to provide for multi-core. So the fact that we make APIs that can run asynchronously or that can run efficiently, we have to provide for both kinds of consumers, whether those consumers come from an SMP where they're another processor, or whether they come from multi-core where they're on the same processor. You know, it's the whole parallelization, making it so that we don't have a lot of lock contention, you know, and these kinds of things that slow down your scalability.
Sure.
And so by virtue of the fact that we already have to scale the memory manager to run on 64 processors and terabytes of RAM, I mean, we've created this foundation that has to run those efficiently. And 64 processors simultaneously making requests to the memory manager have to scale well. So we can't have a one-lane road that they all have to travel on. It means that for multi-core, we've kind of already crossed that bridge in memory management as far as making things able to run in parallel, you know, as efficiently as possible. Not to say there aren't things we couldn't improve, and I'm sure we will
Sure.
as time goes on, but I think it's inherently already well suited for multi-floor.
Fantastic. Excellent. Well, this has been great, and I know we've only touched the surface of this. You mentioned it's a relatively large project, and hopefully we'll be able to talk more about the future without too much speculation.
Sure. Sounds great.
Fantastic.
Thank you.
Great to meet you.
You too.
Thanks a lot.